Hello, today I'm going to present our last project, which is Machine Vision System by KEYENCE. And this uh, presentation is presented by me, myself, Mohammad Munif Hassan, and my fellow teammates, Aladin Ahmed and Sanjidul Ahmed. Now I'm going to the introduction part. Quality inspection for additively manufactured components increasing relies on computer vision techniques capable of detecting subtle geometric deviation and surface anomalies. Traditional manual inspection is often time consuming, inconsistent, and unsuitable for high precision or repetitive tasks. To address these challenges, vision-based metrology system, particularly high-resolution industrial cameras, provide a fast and reliable approach for identifying dimensional defects in 3D printed parts. In this project, a KEYENCE industrial vision system was employed to detect variations in the geometry of multiple 3D printed samples. Although all three samples appeared identical from the top view, one of them exhibited a reduced sidewall thickness. Additionally, one of the samples contained a printing defect that was not easily observable without automated inspection. By integrating computer vision techniques with the KEYENCE camera measurement capabilities, the system successfully identified both the dimensional inconsistency and the print defects. This demonstrates how camera-based vision inspection can be used as a robot tool for defect detection in additive manufacturing workflows. Now let's hop into the objectives. Our primary objective is to apply computer vision techniques to the automated defect detection in 3D printed components using high resolution KEYENCE camera. Measure geometric variations, specifically sidewall thickness differences among samples that appear identical from a standard viewpoint. To identify surface detections and surface defects or irregularities in the 3D printed parts through vision-based inspection. Demonstrate the effectiveness of vision-based metrology as a reliable, fast, and repeatable method for quality control in additive manufacturing. Lastly, validate the capability of the KEYENCE system in distinguishing the odd samples among visually similar parts using quantitative image measurements. In the methodology, the defect detection workflow was carried out using a KEYENCE industrial vision system connected to a laptop running the KEYENCE image processing software. The overall procedure consisted of four stages: system setup, image calibration, region selection, and automated thickness inspection. Now I want to invite my fellow teammate Sanjidul Ahmed to present the next slide.
I'm Shanzidul Ahmed. I'll carry on the rest of the part from here. As the first part of methodology, we'll set up the system and initialize the camera. The KEYENCE camera was first connected to the laptop through the provided interface. After launching the KEYENCE software, the device connection was verified by enabling the built-in illumination function. When the lighting module successfully turned on, the connection status was confirmed, ensuring that the camera and software was communicating properly. After that, we'll calibrate the image by zoom tracks. We'll set the brightness and focus the adjustment. Once the camera was functioning, the zoom tracks calibration module was used to configure optical parameters. The brightness was adjusted to avoid overexposure or underexposure of the printed samples. The focus was optimized to obtain a sharp edge profile, which is essential for accurate measurement. These adjustments ensured that the camera could clearly capture the sidewall boundaries needed for dimensional inspection, which we can show the photo of the part adjusting the zoom text in below. Next. After that, we'll select the region using a positioning tool. After calibration, the position tool was used to define the region of interest. The region of interest corresponds to the specific area where each sample would be placed during inspection. Establishing a fixed region of interest allowed consistent measurements across all three printed parts. This also ensured that only the relevant edges were analyzed during thickness verification. We can see in the picture. After that, okay. After that, we'll select and configure the inspection tool. With the region of selection defined, the inspection process was configured using the edge wide tool, which measures the distance between the detected edges from the in the captured image. One of the 3D printed samples was selected as the standard reference part. The edge wide tool was calibrated by adjusting thresholds and edge detection sensitivity to match the true thickness of the reference sample. The reference configuration formed the baseline for evaluating the remaining samples, which you can see from the picture. Next. After that, uh, from this part, we'll do the flat orientation inspection.
So
To
Okay. From
invite
this part,
Aladdin Ahmed
okay. From
to
this part,
present this part
yeah,
and
yeah.
kindly, yes, Sanjidul Ahmed, please.
Yeah. From this part, Aladdin Ahmed will present. Thank you.
thank you, Shanju Ahmed. So let's discuss actually what we did. We first put a sample as in a standard, and then we then inspected others models to see whether it passed as standard or not. So for the first one, when the object was in flat orientation, it passed because the thickness was same. It was same as the standard. And for to select the standard, we already put it the upper limit and lower limit. Although we calibrate the upper limit and lower limit at a certain point, and by the calibration, we ultimately get our result. And for the first one, it passed. Let's move on the second slide. So in here, what we did actually, as previous, we we uh, put our object on the on focus, and this time we put it in side orientation, and we measured the thickness as the standard, and we also calibrated the upper limit and lower limit. And after that, we tried with two model, one with the same thickness as before with the standard, and another with the smaller thickness. So for the same thickness, we got that the object passed, but for the smaller thickness one, it failed, as we can clearly see from the status at the top right corner. For the small thickness one, it failed, and for the perfect thickness one, it passed. Let's move on the next slide. And we also detected additional printing defects because uh, one of our model had some defects at the corner of the part, and we also checked it with the standard, and we saw there is there is some defects and there is some the object actually crossed the limit, and that's why it failed. And we can clearly see it from the top right corner that it failed. Let's move on the next slide. And in conclusion, we're supposed to figure out which model passed and which model didn't, and we put a standard, and we took one model as a standard, and the result was the same as we expected, and we detected what we're supposed to, and this will clearly help in manufacturing process and all. Let's move on to the next slide. Thank you everyone.